Welcome back to CypherSpaceCore. In the previous episode, we explored modular arithmetic and congruence theory. Today, we move deeper into one of the most important functions in number theory, Euler Totient Function. This is the one of the core mathematical idea behind RSA encryption and modern public key cryptography. Think of Euler Totient function like a mathematical filter inside modular arithmetic. It defines which number can safely interact inside cryptographic system, and this single idea becomes one of the foundation of RSA encryption. Firstly, we exactly define what is Euler Totient function. We represent it using phi of n. Phi of n tells us how many integers smaller than n are coprime with n. What does coprime mean? Two numbers are called coprime if their greatest common divisor is 1. Simply, they share no common factors except 1. The main usage of Euler Totient functions are in RSA key setup, where we find phi of n, and in Euler Theorem, where we find a raised to phi of n congruent to 1 mod n, and in Pivot Key Generation, we find d equal to inverse of mod phi of n, where here we find the inverse of based on modulo phi of n. And next we define phi of n. Phi of n is equal to k such that 1 less than equal to k greater than n, GCD of k comma n equals 1. This means count of phi of n counts how many integers k satisfy, that is 1 less than or equal to k less than n, and the GCD of k comma n equals 1. Euler Totient function counts how many numbers from 1 to n minus 1 shares no common factors with n. For example, phi of n. Let's compute phi of n. We check numbers from 1 to 11. For 1, GCD of 1, 12 equal to 1, which is coprime. For 2, GCD of 2, 12 is 2, which is also coprime. Likewise, we find all GCD of each number with 12. And lastly, we find only 4 numbers are coprime with 12. So phi of 12 is 4, which are 1, 5, 7 and 11. Now let us study the most important formula used in computing Euler Totient function. First case is prime number. If p is prime, phi of p equal to p minus 1. Because the prime number has only two divisors, 1 and themselves. This means every number smaller than a prime is automatically coprime with it. Phi of 7 is 6, phi of 13 is 12, and phi of 17 is 16. Suppose second case is prime powers. Suppose n equal to p raised to k. Then phi of p raised to k equal to p raised to k minus 1 into p minus 1. Think of it like a filtering multiples of p. Those multiples shares factors with n, so they are removed. Let's find phi of 8. 8 equals 2 raised to 3. So phi of 8 equal to 2 raised to 2 into 1, which is 4. Next example, phi of 27. 27 equals to 3 raised to 3. Therefore, phi of 27 equal to 3 raised to 2 into 2, which is 18. And third case is multiplicative property. Here, phi of m into n equal to phi of n into phi of m. If GCD of m comma n equal to 1. This means Tollen values multiply independently when the numbers are coprime. For example, since GCD of 2, 3 equal to 1, then phi of 6, that is phi of 2 into phi of 3, 1 into 2 gives 2. This property works only when GCD of m and n equals 1. Third case is product formula. Here we find phi of n equal to n product of p bar n into 1 minus 1 by p. Each prime factors remove numbers divisible by it. For example, 5 of 15. Prime factors of 15 are 3 and 5. Applying formula, 5 of 15 equal to 15 into 1 minus 1 by 3 into 1 minus 1 by 5, which is 8. So the coprime numbers are 1, 2, 4, 7, 8, 11, 13 and 14. Now we reach one of the most important theorem in number theory, Euler Theorem. The theorem defines a raised to 5 of n congruent to 1 mod n. This theorem is the fundamental to RSA decryption. Without Euler theorem, RSA would not mathematically work. Now let us understand what this theorem actually says. 5 of n count how many numbers are coprime with n. And when a number is coprime with n, modular exponential start behaving in a cyclic way. Think of it like moving around a circular track. As a power increases, value grows, wrap around and repeat, and eventually cycle back again. Euler theorem tells us exactly when that cycle returns back to 1 modulo n. Imagine repeatedly multiplying a number by itself inside a modular arithmetic. For example, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, mod 5. The value does not increase forever normally. Inside, they wrap around repeatedly because of modular arithmetic. And eventually, the cycle comes back to 1. That repeating behavior is the core idea behind Euler theorem. Why GCD of a comma n equals 1? This condition is extremely important because only coprime numbers have modular inverse stable cyclic behavior and predictable modular structure. If the numbers share common factor, the modular cycle breaks and Euler theorem may no longer hold. Now let's connect it directly to RSA. In RSA, during encryption and decryption, we repeatedly perform modular exponential. For finding D private key, or in encryption, we find message raised to E mod n. And during decryption, we do E raised to M raised to E whole raised to D equal to M raised to ED mod n. Euler theorem guarantees that this process eventually returns back to original message. That's why Euler theorem becomes one of the foundation of the public key cryptography. Next, key properties of phi of n. Now, property 1. Phi of 1 equal to 1. Only 1 is a coprime with 1. Property 2. Phi of p equal to p minus 1. For prime number, every number smaller than p is coprime with p. Property 3. Phi of n is even for n greater than 2. Except for very small cases, Euler Totient values are always even. Property 4. Phi of m into n equal to phi of m into phi of n if GCD of m comma n equals 1. This multiplicative works only when the GCD numbers are coprime. Now let us understand why Euler function are essential in modern cryptography. RSA security depends on it, as it defines phi of n equal to p minus 1 into q minus 1 cannot be computed easily unless we know factors of n. So without factorizing n, an attacker cannot compute phi of n. And without phi of n, attacker cannot compute the private key. Next, in keys generation. In RSA key generation, D equal to inverse of mod phi of n. This step is impossible without knowing phi of n. Proving RSA works. In Euler Theorem guarantees the current RSA decryption. Euler Theorem guarantees correct RSA decryption, that is m raised to ed congruent to m mod n. This mathematical relationship is the reason encrypted message can return back to original plain text. Next is Carmichael function, that is lambda of n. This function is called the Carmichael function. It represents the smallest positive exponential cycle that returns back to 1 modulo n. A raised to k congruent to 1 mod n. Often, lambda of n is less than or equal to phi of n. So the advanced RSA implementation often prefer lambda of n because it is more efficient. Today we studied at Euler Totient Function, Coprime Computing, important Euler formulas, Euler Theorem, RSA application, and Carmichael Function. Euler Totient Function is one of the first bridge between the pure mathematics and real-world security. It transforms number theory into practical cryptography security. Thank you for watching ZypherSpaceCore. If you found this lecture useful, subscribe and continue our journey from number theory to advanced cryptography.